Good afternoon, everybody. Today we're going to do an optimization problem. And so we have a tailoring company that produces wool and cotton jackets. And at the tailoring company in question, we have wool jackets that require 2 hours of cutting and 4 hours of sewing to put together. And then on the other hand, we have cotton jackets that require 4 hours of cutting and conversely only 2 hours of sewing to produce. So altogether at the company, they can cut up to 20 hours a day in total, and they can sew for up to 16 hours a day. And so these are going to impose restrictions on how many of each types of jackets we can reasonably produce in a day. Next, we're told that the profit is $34 for every wool jacket sold and $31 for each of the cotton jackets. And so we are tasked with figuring out how many of each this tailoring company should produce per day to maximize their profits, right? So first and foremost, let's start with our variables. I'll use X for the number of wool jackets sold for simplicity's sake. And I'll use good old Y for the number of cotton jackets sold. Now, with our variables properly defined, we can move on to our restrictions. It takes 4 hours of cutting for a cotton jacket, and it takes 2 hours of cutting for a wool jacket, and we can only cut up to 20 hours a day all in all. And so our first restriction I'm going to write is going to be 2 hours for each wool jacket. That's our X variable, right? 2 hours for each wool jacket that is produced. And so that means 2X plus 4 hours of cutting for each cotton jacket that's produced. That means 4 hours for every Y, and so plus 4 times Y can be no greater than 20, right? We can only sew up to 20 hours a day, and so 2X plus 4Y needs to be less than or equal to 20. I'll even make a note that this is from the cutting restriction. Okay. Whoopsies. Cutting. Next, we'll have a second restriction from the sewing. So the first line says that wool jackets require 4 hours of sewing and cotton jackets only 2 hours of sewing, and we can sew for up to 16 hours a day. So this one you might be able to write on your own right away. 4X plus 2Y is less than or equal to 16. Again, this is from the sewing necessities. Now, we can also state that, of course, we can't sell decimal amounts or negative amounts of jackets. And so obviously we can say that X and Y both need to be restricted to whole numbers only, right? For obvious reasons. After that, we will have an objective function that we have to consider. Our objective function is the thing we're trying to maximize. And for us in this case, we're trying to maximize profits. And so our objective function that I'll write over here, our objective function will be one for the profits, and our profits will be made up of $34 for each wool jacket. That's our X variable. And so $34 times however many wool jackets we produce, hence 34X. And also $31 for each cotton jacket produced. That's our Y variable, so plus 31Y. And again, that's the function we want to maximize, we want to optimize. Okay. So now we want to graph these inequalities. These are inequalities, right? And we're going to look for a feasible region and then test the vertices of that feasible region for our optimal solution. And so, as we always do, I'll label our graph with an X and Y axis. First off, we're used to graphing lines in slope intercept form, so we should take the time to change these inequalities to be in slope-intercept form, i.e. in y equals mx plus b. And so from that first inequality, you gotta leave it in green, we can write this as y is less than or equal to, I'm gonna skip over the algebra, but you'd subtract 2x on both sides, and then you divide everything by 4, right, to get the y all by itself. And so if you do that, you'll have negative 1 over 2x plus 5, right? After subtracting 2x and then dividing by 4, 2 over 4 is negative 1/2, and rather negative 2 over 4 is negative 1/2, and 20 divided by 4 is that plus 5. And then from the second inequality, again, putting it into slope-intercept form, getting the y all by itself, subtract 4x and then divide by 2. Negative 4x divided by 2 is negative 2x. And 16 divided by 2 is 8. And so here are the two lines that will form the boundaries of our feasible region. Now they're both less than or equal to, and so we can make solid lines for the boundaries. I'm going to go up by 2 so that we have enough space to see everything. And I'll have the x only go up by 1, like so. So let's start with the first line. We're going to graph this line as the boundary of our feasible region. And so negative 1/2 x plus 5, that's a y-intercept at 5 and a slope of negative 1/2. And so I can extend this axis a little bit, give us a bit more room to play with. That's our x-axis. That'll be 9 and finally 10. I did that because y-intercept at 5 with a slope of only negative 1/2 means that we're going to go down by 5 and over by 10. And so this here will be our x-intercept, like so. And we have to be below that line because y is less than or equal to negative 1/2 x plus 5. And so we're now restricted to below this red line on our graph. Next, we have y is less than or equal to negative 2x plus 8, y-intercept at 8, and then a slope of negative 2. So down 2 over 1. So y-intercept at 8, down 2 over 1 means down 8 over 4. And this will be our second boundary. And now x and y are both restricted to whole numbers. So we're not going to shade in the region, right, because we can't have any decimal solutions. And so we should dot all the solutions. So we should have dot here, 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 so on and so forth, right? This is tricky to do perfectly, but it's hard to actually see. Yeah. That looks okay to me. And then maybe one more here. Yeah, we'll leave it at that. And of course, here, here, and here. And so now we want to test the vertices of our feasible region, right? This shaded region is what we call our feasible region, right? This is where somewhere our optimal solution is going to lie because we need y to be less than or equal to, meaning below both lines simultaneously. And so now we can test a few different points. We could test the origin. This is likely to be the case maybe if we're minimizing, but obviously we're not minimizing profits here. We want to maximize profits. It's unlikely that selling no jackets is maximizing profits. Likely we're going to use this point here, or this point here at the intersection of these two lines, right? So this point is clearly at 4, 0. This point is clearly at 0, 5. However, this point will have to do a tiny bit of work to find its coordinates because it lies at the intersection of these two equations, i.e. when negative 1 over 2x plus 5 is equal to, right, when the equation of the first line is equal to the second line, right, is equal to negative 2x plus 8. And so now you can do your algebra, add 2x to both sides, so you'll have 1.5 x plus 5 is equal to 8. Subtract 5, 1.5x is equal to 3. And divide by 1.5, divide by 1.5, and you find that x is equal to 2, which looks okay. My graph is not perfect, apparently. Making sure I didn't make any mistakes here. Negative 1/2. Adding 2 means positive 1.5x. Subtracting 5, that's 3. This seems fine. So it looks like if I made my graph perfectly, this would be the point of intersection. And so that'll be at x is equal to 2. And to get the y coordinate, since that point lies on both lines at the same time, it's their intersection, it lies on both, we can plug x into either equation and get the y coordinate. Then they should give us the exact same one. So if x is equal to 2, negative 1/2 times 2 is negative 1, and negative 1 plus 5 is 4. In the other one, negative 2 times 2 is negative 4, plus 8 is also positive 4. Right? I'm going to leave that out for the sake of having enough space, but either way you slice it, you'll get a y coordinate of 4 as the intersection of these two lines. Okay? This is a nice argument for making your graphs look really, really nice, and maybe using a ruler. So with that said, now we have all 4 vertices of our feasible region accounted for. So we can test to see which one optimizes our objective function of profits. And you might be able to see quickly that it's going to be the 2,4 solution. If you want to test a few points, feel free. So I like to encourage my students to look at a few test points. You can plug in x equals 0, y is equal to 5. Throw those values in for x and y, respectively, in the objective function. So P profits would be 34 times 0 plus 31 times 5. And so that would give you profits of $155. $155. That's very messy. I'll leave it at 155. Okay. Goodness, that's messy. Let me clean that up a bit. There we go. Again, if you plug in 4, 0, you'll get something a little bit less than that. But if you plug in 2, 4, then you'll get P is 34 times 2 plus 31 times 4. And so the profits will be 68 plus 124, which is $192 profit. And that is, in fact, our optimal solution. And there we have it. We've arrived at the end of our problem. So again, always start by defining your variables. Sometimes this can really, really get you out of jam if you can't exactly picture how the restrictions are coming about. Having your variables clearly defined can make that task a lot simpler. From there, we write our restrictions, even the whole numbers if it's appropriate. Then we like to convert our restrictions into a form where we can graph them readily. Graph the restrictions, either dot or shade in the feasible region, test the vertices, the corners of your feasible region, and see which point optimizes your objective function. And there we have it. I hope that helps. Thanks for watching.